of this workshop. Today's theme is to make connections between the fields of machine learning and program synthesis. And it's my great pleasure to welcome Professor Jerry Zhu from the University of Wisconsin-Madison. Jerry is a well-known figure in the field of machine learning and more broadly in AI, and has done many wonderful contributions to those areas. But I got to know Jerry actually when we were grad students at CMU more than 20 years ago. Even back then, I thought his research was very cool, and I've continued to be a big fan of his work. And about 8 years ago, we had the pleasure of collaborating as co-organizers on one of the very first of the recent batch of Darkstool seminars connecting machine learning and formal methods. This was back in 2017 at a time when nobody was really doing that. And we can actually directly connect many of the active collaborations we see between participants who came there and research programs that are happening today. So that thread is continued. And in particular, one of the connections that I just mentioned is between a sub-area of machine learning called machine teaching, which, as Jerry will explain to you, is kind of the inverse problem of machine learning, and program synthesis. And particularly, we think machine teaching is a very fruitful area to also develop theoretical foundations of program synthesis that is based on machine learning. So it's, again, my great pleasure to welcome Jerry. He's going to give us a talk to teach us about machine teaching. And hopefully we'll make more connections in this workshop as we did in the Darkstool seminar 8 years ago. Okay, welcome, Jerry.
Thank you very much, Sanjit. Thank you everyone for coming. So as you can see, I'm going to talk about machine teaching, and the word, if it's foreign to you, it's not going to be, I hope, very soon. So let's dive right into it. And I'm going to assume people have an understanding of what machine learning is, but I'm going to try to start with this basic example. So on top, I'm going to demonstrate with a very basic machine learning problem. So you are given the data set. I'm going to call it the training set D, and let's call this the classification problem. So you have training item, first item X1, that could be a feature vector of whatever, and Y1 is the class label. And for this talk, I'm often going to just do binary classification. So Y1 is plus or minus, fine. And for the sake of illustration, X is going to be in one dimension. So you can think of it as like one-dimensional embedding of whatever document, spam versus not spam, etc. So that's going to be my data set, and I will have n of those. And if you're familiar with machine learning, we typically assume that the data items are sampled IID from the underlying distribution that describes your problem. So for example, maybe the X is uniformly distributed over this interval, and Y is really determined by a true threshold, W star. So we're considering threshold classifiers. W star is a true threshold, so that to the left, everything should be negative. To the right, everything should be positive. Okay, so that's the setup. Now, the task of machine learning, as we know, is we design learning algorithms. In this talk, I'm going to call this the ALG, the learning algorithm, such that, for example, let's just say we're using large margin classifier, support vector machine, that kind of stuff. But also you can think of, for this particular case, think of it as one nearest neighbor classification. It's the same thing in 1D. So what do we do, right? We design such an algorithm, and we feed it the training data set D, and it's going to spit out an estimated decision boundary. So in my case here, by randomness, maybe I sampled from uniform distribution, I got 3x, and they're corresponding Y's determined by the true decision boundary, and of course, large margin. So it's going to look for the nearest, the innermost negative positive pair, put an estimate in the middle and say, hey, that's where I think the decision boundary is, call that W hat. Okay, so that's the business of machine learning, pretty much. And if you make reasonable assumptions such that, for example, D is IID samples, then you get nice learning theoretical guarantees. For example, in this case, we can say that in expectation or with large probability, the distance between what you estimate and what the true boundary is, that distance is on the order of 1/n, where n is the training set size. Okay, so that has been what's going on in machine learning as a simple example. Now let's move on to the subfield of machine teaching, and we're going to turn the table around. So in this problem, it's very different. I'm the teacher now. I know W star, the true decision boundary. There, machine learner didn't know it. I know it. And I know what the student is, and that is the learning algorithm. Okay, so for example, I know it is doing SVM. My job, however, is to design a training set D, such that when I feed that specially designed training set to the learner is going to spit out the correct W star. Okay, so if you think about that, right? So in my case here, if I know the true boundary is here, I could create a very special training set that really puts one negative, one positive on across the decision boundary, true decision boundary, and make them very close. Okay, that seems reasonable, but you also immediately see that this data set D is not a traditional randomly sampled IID data set. It's special, okay? So I'm assuming that the learning algorithm didn't know that. It still assumes whatever assumption it wants to believe in, such as the training data set is IID and it's going to proceed and do its stuff. I am not going to worry about that. I just assume I know what the algorithm is going to do. Okay, so this would be a good data set that fits this. And this is going to be called a teaching set. I'm going to use this and I'm going to teach a particular learning algorithm. Okay. But you immediately also see that teaching set is not unique. For example, if I know the algorithm is large margin, then I could create an alternative teaching set where I just pull those two training items apart. As long as they're symmetric around W star, that's totally fine. Again, the learner is going to return W star. And furthermore, you can also just create a training set like this with a lot more items. That's also fine, because by the nature of this particular algorithm, it's only going to care about the innermost pair and put the boundary in the middle. So this seems like this problem is not super well defined. Okay, so we'll see how this relates. But I want to immediately explain why this could be relevant, especially from a AI security perspective. We could think of this as the task of attacking a learning system through training data. Okay, so obviously, if this is, for example, if this space is document embedding, email embedding, and this is your spam versus not spam classifier, and there's a true threshold for it. And if somehow an attacker can feed in training data that's specially designed, such as this, it can really move where that positive negative pair is and force the spam learner to learn a different threshold, right? So that was the concern, and we will see this perspective again and again. All right, but let's come back to another alternative view of what contrasting machine learning and machine teaching. So on the left-hand side, this is how we think of the learning algorithm. This circle is the space of training data sets. So each element is going to be a particular training set, not necessarily IID, it's just a bunch of XY pairs. And we view this algorithm as a function that maps a training set to a learned model. So if you feed it D, it's going to get some W hat model, right? So that's machine learning. And we want to design good algorithms so that this estimate is close to the true W star in some statistical sense. Machine teaching is really the inverse problem. We start with a target model W star. This could be the true model, as I was saying, or it could be an adversarial target. It's like a especially bad model, doesn't matter. And we know the algorithm, so we're interested in the inverse of this algorithm that looks for the set of training sets here that each one of them, if you use algorithm, they will go to W star, right? So this is the image of the inverse image of, that algorithm. Pardon? It might not notice. It might not exist. A very, very, very good point. So in general, you cannot hope to hit this exactly, and you can relax it with various like distance notions. Okay, excellent point. All right, but assuming it exists, as we saw previously, there could be multiple data sets that map to W star, and the teacher may have preferences, and those are the contours. There might be, for example, hey, I prefer the smallest cardinality D to do this job, and so that would be the preferred training set. Okay, so that's that. Let me know if anybody want have thoughts at any moment. All right, so I'm going to try to push a lot of content, and when I was preparing the slides, I find myself very disoriented. So this is my attempt to organize things. We will gradually build this map of concepts. So far, I have been discussing machine teaching as an inverse machine learning problem, where the learner is a supervised learner that pretty much does a convex optimization problem. Think of it as large margin. You have your hinge loss and so on. The teacher may prefer more cardinality of a teaching set. Right, so that's so far the setting, and we will see many related but different setup for this kind of inverse problem. Okay. Now, at this moment, let me just pause a little bit, and if you come from a more machine learning background, you might ask, like, why would anybody care about this? And the question is, why not, if the teacher knows the true model W star, why not just give it to the learner and call it down, right? So for example, if W star is your deep learning model weights, why not just send the weight to the receiving end? So this question is really motivated by two main, in my view, main application areas of machine teaching. One is actually in human education, where the teacher is literally a human teacher, and the student is a human student. But we're going to model how the student learns as a learning algorithm, okay, in its head. So the teacher cannot really just burn neural weights into a student's brain, not yet. People are working toward that, but not yet. It's much easier to just give student whatever teaching experience. And this is what we went through as students, lessons, exercises, and so on, so that the student applies the learning algorithm there and changes its own, wires its own brain, right? So that was one motivation for why not sending W star directly. But more relevant for this workshop, the same thing can be said when you have a learning system. That learning system receives experience from the external world through some API, for example, but it usually cannot receive just the model itself. If you are not the creator of this, you cannot send it that, but you can send it experience and use the experience to control the state of the learner. Yes.
We think about the teacher designing W star. Is it easy to specify?
Excellent. So throughout this talk, I'm going to assume W star is going to be either a true model that is actually known to the teacher. And this is reasonable in the case of, say, education. As teachers, we really know what state we want, knowledge state we want student to arrive at. In the attack case, this W star is going to be constructed by the attacker for a certain purpose. For example, in the case of spam filter, we could say W star is just a particular threshold that the spammer, the attacker, wants your spam filter to eventually take, such that maybe it allows certain kinds of spams to go through your filter. So we will assume this is given. But we can have a discussion later. For now, let's just think W star is given. So that's why it's also not machine learning. We're not trying to estimate W star from nature. We assume W star is already known to the teacher.
Maybe W star is a threshold makes sense. Sorry about that. Maybe W star is a threshold is easy to specify, as you gave an example, but if it's a set of parameters, I just not sure how that would.
Yeah, hold on to the thought toward the end. You will see many examples, but I agree with you. In general, it could be difficult to specify. But we often take the machine learning view, like the blue star, for example, if it's a neural network, even though it's hard to specify its billions of parameters, but it's there. Okay, conceptually at least. Thank you. All right, so yeah, that's what we just discussed. So we're viewing the machine teaching problem as either a tech problem or as education in humans. And and by the way, for the record, because we live in strange times, I want to say that this is not saying our educators are attackers of our students. It's just that the education problem and the adversarial attack problem, they somehow with completely different purpose, right, share some underlying mathematical formulation. Okay, so that's what this is trying to say. All right. And for those of you who are into machine learning, I want to highlight one more thing so that we see very clearly that machine teaching is not learning. So we already saw the top panel and the bottom panel. That was when the learner is training on the training set that's what's called passive learning, where the training set is ID sampled from the environment. So you get randomness. And because you get let's say this is a uniform distribution over this interval. That's how you sample the xi's from your data. Then it's easy to see if you want the estimated large margin decision boundary to be, epsilon close to W star. You need roughly 1 over epsilon training items. That's because you can more or less think of the training items as evenly spaced, even though they're not, but think of them as evenly spaced. Then the innermost one is kind of like 1 order 1 over n. So you flip it, that's your sample complexity. You need this many training items to get that precision. Bottom one, we saw that, right? So the teacher can design this very special training data set, and it can place this very close to each other so that, it doesn't matter what epsilon you require. We can teach it with a training set with 2 items. So this is really order 1 sample complexity. Okay. But for those of you who are familiar with active learning in machine learning, it's the problem where the learner can actively query X points and ask the environment what's the true label. Okay. That is viewed as a very efficient way to do learning, better than passive learning. In the special case of one-dimensional threshold classification function, active learning reduces to just binary search on the learner's side, in the sense that the learner looking at the problem would say, I don't know where W star is, but I know it's a threshold with negative on the left, positive on the right. So what I should do is I should query the midpoint of the interval first, and I will ask the environment, what is the true label for this one? And this one, because it's to the right of the true decision boundary, the environment will say it's positive. Now, with this knowledge, the learner can exclude all thresholds on the right. So now it essentially have a remaining unknown uncertainty in the threshold just to the left. So you should do the binary query in the middle again here. And if this is negative, the environment says it knows the threshold is in between, and so on and so forth, right? So, so obviously, yes.
So I think it's quite easy to understand when you see it in a 2D, but how does I can picture this in higher dimensions, right? Do you want to have some separating hyperplane or?
Yes. So the analogy in the high D is going to be separating hyperplanes for this. Yes, but you get uglier coefficients than this. This is much, much easier to understand in 1D. The point, however, is this. Despite being very good at learning with active queries. To learn to epsilon precision, this learner still need to query log 1 over epsilon points, because it's doing binary search and until that gets to epsilon, right? So it's going to, if you contrast this with what the teacher can do, there's still a dependency on this epsilon. And the reason is this is a price that the learner has to pay for not knowing where W star is. Of course, it doesn't know where W star is. That's the learning problem, right? So this is the price of learning. And that's why the teaching problem is different. It's a different problem because we start with W star and we just need to encode it for the learner. Okay. Oh, yes. And now let's come back to this. And here we require 2 teaching items for my specific learner. Let's zoom into this O1 business. And it's going to be described by a quantity known as teaching dimension. Okay, so for this, however, I'm going to revert a little bit back to a different type of learner, and in fact, slightly simpler setting. I'm going to assume the universe, instead of being a continuous interval, it's just going to be, in my case, n points or 6 points to be specific, and they're evenly spaced, imagine, over my interval, okay? And each row corresponds to a particular threshold location, okay? Such that, for example, W1 is a threshold that's kind of like all the way to the left, so that every item is going to be classified by this threshold as positive. While W2 puts the threshold kind of here, so that it classifies X1 as negative, but everything else as positive, and so on and so forth, right? So as you can see, I'm also equating a threshold with the binary classification function that it induces now. So I'm going to take now the view that each W is now a classification function. So each row is a function over my universe of 6 items. Okay, so I don't have too many threshold functions, really. I only have 7 of them in my very tiny universe. All right, let's also say that W3, the green row, is the true threshold that the teacher knows. This is the true threshold. We should classify the first 2 items as negative and the rest as positive. Now the question is, how should we think of, I mean, just by inspection, we sort of know that, hey, the teacher really should pick X2 negative, X3 positive as the teaching set. How do we think of that? So one very useful way to think of this is to think of a set cover problem. And let me explain. The set, the universe that we're trying to cover is actually all the thresholds. That's not my target threshold. So we want to cover the universe of these 6 functions. Okay. And what are the set that we have available? Well, each item, such as X1, actually induces a subset. So now let's read the column. The column of X1 says this. X1, the true classifier, will classify it as negative. And X1 says, W1 will classify me as positive. W2 will classify me as negative, and so on and so forth, right? That means if I teach with X1 and the true label negative, that pair, I will be able to eliminate this W1 element because it's inconsistent with this label. But I cannot eliminate W2, W4, etc. Those are consistent with the label, the true label of X1. Okay, so that means X1 actually is equivalent to a subset of my element that is this subset. It is the subset of W1. If I use X1, that is like saying I have a subset that's W1 that I can use it to cover this universe. If I have instead, if I use x2 and the true label negative to teach, I can eliminate W1, W2. So that the subset of W1, W2 is the subset induced by x2. So those are the yellows in each column. Now we have, this is a subset, subset number 2, subset number 3, 4, 5, 6. We have 6 subsets. We're trying to cover the purple universe. Set cover problem, find the smallest number of subsets to cover your universe. That will work out to be x2 and x3. Okay. So this is interesting. It differs from what we said earlier. I want to point out one thing. So let me go back to many slides ago. Here. For example, I said this could be a valid teaching set with only 2 items as well, right? But here, that's kind of like saying, hey, you can use X1 and X4 to teach. The reason now it is no longer okay to use X1 to X4 to teach is because I subtly changed my learning algorithm. My student is now different. Previously, it was a large margin SVM type of learner. Now I changed it to be this version space learner. That just means given everything here as your initial hypothesis in the student is simply going to eliminate any hypothesis that's inconsistent with the training set it has seen so far. So if we were to teach with X1, X4, this student will still have in its hypothesis space, the version space. The remaining version space is going to be W2, W star, W4, that subset, right? So for this learner, we need stronger teaching set, and that is recovered by the set cover problem. And the cardinality of your set cover solution is known as the teaching dimension for this task. So here, the teaching dimension for teaching W star is going to be 2 because that and that is your cover solution. Yes.
Are you going to give a formal definition of teaching dimension?
No. So
okay.
I think I would defer that to Sandra's talk.
I see.
She's going to cover it.
I
think this is absolutely important, but I didn't do that. If you want me to, I can.
No, because I'm just asking because usually it is given in a way that's agnostic to the algorithm, or maybe just for version. Depends on the presentation, but I guess Goldman and Kearns is specific to consistent learners.
Exactly.
Right. And so I just wanted to understand if there are
that's right.
notions.
So your insight. So the Sanjit's question is this. So in the original paper by Goldman and Kearns, the learner was actually kind of implicit because at that point it was assumed to be this version space learner. It's not any of the learner I'm going to talk about later. Okay, so because of that, it really is precisely this setting. Okay, so the classic teaching dimension is only defined for version space learner.
I just wanted to make a comment then, just to connect it to some stuff earlier in this workshop. So in addition to the connections that Jerry drew, the applications of machine teaching, there is a further application to program synthesis, which uses this notion of teaching dimension that he just described on the slide, which is that the teaching dimension for version space learning, for consistent learning, can be proved to be a lower bound on the number of iterations in counterexample guided inductive synthesis, in program synthesis. And the connection is actually quite simple to see, but once you have the setup. But I just wanted to mention that is actually a direct connection between results in machine teaching and theory of program synthesis.
Just asking for the cultural, why choose the word dimension and not teaching cardinality, let's say?
All right, so that's a question for Goldman and Kearns. But there's a good cultural reason, because before that time, in the machine learning community, the hot thing was VC dimension. And this teaching dimension was meant as a buzzword to contrast, in my opinion, it's to contrast with VC dimension. And we will see that on the next slide. So let's go there. Yeah.
Just a clarification question. Version space, how should we think about it? Is it's finite versus not?
All right, so sorry. Version space itself is just okay, so let's start from hypothesis class, right? So we're hypothesis space of a learner, and that's going to be every column, every row here, all the rows. That's the starting version, hypothesis space. Version space is going to be the subset of those that is consistent with all the training data so far, okay? And the version space learner is a learning algorithm that simply eliminates any hypothesis from the original hypothesis space that's inconsistent with any training data. So it's very simple. Yeah. All right. Coming back to the cultural question, right? Contrast with VC dimension. I think it's worth, this slide to see that they're quite different animals. So on the left-hand side, we have this table, again, same story. The concepts are really just classifiers, and the columns are different items X, right? So it's the same story, but let me point out what this is doing. This first concept classifies every item as positive. And then the remaining one, you see there's a diagonal of one negative classification or label for a different item, okay? The reason that this is interesting is the following. As teaching, right? If you teach, say, this, if you want to teach this concept to a learner, it's very easy. You can just say, the last item should be negative. That's what the teacher says. That's it. So you just need one teaching item. This is true for all these except the very first one. Now you think about it. Because the teacher cannot lie, it can only say, this item, its label is positive. That would be one teaching, right? Now the trouble is that leaves a whole bunch of possibilities. The version space is quite large. In order to actually specify the first concept, the teacher has to use all instances and say each one of them is positive. So the teaching dimension in this case for the first concept is going to be the number of items. So you can make that as large as possible. In contrast, as we can see, this thing is such a diagonal thing, is such a poor family of hypotheses, it cannot really shatter to points. So the VC dimension is just one. Okay, so you have this instance where teaching dimension can be arbitrarily larger than the VC dimension. But on this problem, let me explain this again. We don't have the nasty first row anymore. We just have this diagonal, positive here. Doesn't matter, but everything else is negative. Then we have additional log n items, and this is just a truth table of those log n items. Why? We're constructing a problem instance where the VC dimension is going to be log n here because the hypothesis class shatters the right-hand side points here, okay? But because we have this diagonal structure here, the teacher can just use this as an index, right? It can teach with that specific item and say that is positive, and that uniquely index into a concept. So that's why here, the VC dimension can be arbitrarily large, but the teaching dimension is one, okay? So the two concepts are not, apparently under this version space learner, they're not quite in order. They flip-flop. Okay, so and also there is the possibility of okay, so let me take a step back. To get a more interesting understanding, this research community represented by Sandra's talk at 2 p.m. Is trying to improve or enhance the learner so that it's reasonable, but go beyond just version space. Okay, so when you give the learner more power, you can say more between the relation between VC dimension and a different notion of teaching dimension. So that's going to be in Sandra's talk. There's also, if you start to do that, there's the concern of the teacher and the student start to colluding by so-called coding trick, in the sense that if the teacher and the student agree beforehand that I'm going to totally ignore what's the truth table here altogether, but I'm going to use the index of the item. Don't even care about the label. If the teacher says, if I use item X1 to teach you, and I will use a teaching set with only one item, we agree that what I meant is concept C1. If I use X2, what I meant was X2, and so on. That would be a coding trick, and it's collusion. It's viewed as not interesting. So that's what Sandra is going to talk about. It's going to be without such collusion. And what can you say about the relation between VC and the teaching dimension?
I just wanted to make in the interest of the workshop, I think we're going to extend the slot to about 10 o'clock. So you have more time.
Thank you.
Okay. And thanks to Elizabeth for being flexible with that. Okay.
Thank you very much. Because I'm only like 1/3 through. But the rest, I think I can go quickly because the remaining things get more specific into specialized machine learning settings. So I can go through the remaining at a much faster pace. But I do want people to see like the connection so far because I think it's really cool. All right. So yeah, that's what we just did is version space learner. But let me go back to convex learner. Okay, this is what I mean by, now I'm going to get into things that are more common in machine learning practice, but can we still talk about teaching? So I'm just going to give you some special examples. So the setting is the learner is doing batch convex learning, meaning that it takes a training set as a whole batch, and it has a convex loss function. It tries to minimize that convex loss function to arrive at an estimated model. So perhaps the easiest one to think about is just regression setting. We're doing regression. The learner is doing not ordinary least squares, but with a two-norm regularizer. So that becomes a rich regression problem. So what we're going to assume is this is the student. The learner takes the learner's algorithm is essentially penalized least squares for regression. Okay, so just think of everything as 1D if you like. If that's the algorithm, and if the teacher wants to teach a W star, okay, a target vector, this in 1D would just be a slope. It's a target slope. Question is how many training items would be needed for the teacher to do so? And the answer is 1. The teacher could do this. It designs a training set with X1 being some arbitrary non-zero constant times W star. And the label is set to be this lambda, which is the regularizer weights, norm square of what it used here divided by A. So you do some mental cancellation, you see that this actually doesn't live, this item does not live on the line of W star. It is slightly off. Why? Because the teacher has to anticipate this regularization. The regularization pulls the W estimate toward 0, and the teacher is counterbalancing that. It's anticipating that, designing a Y that's slightly kind of larger so that it gets pulled back. Okay, so you could do that. And notice here, the teacher is not truthful, meaning that it's teaching item Y1, the label is not on W star. Okay. Let's take another example, support vector machines, but in d-dimensional space. So imagine 3 dimensions. Support vector machine, as we know, it finds the large margin hyperplane to separate positive and negative, right? So if you want to teach a particular decision boundary, how many, if the teacher can construct labeled training set, how many items would be needed? Turns out it's 2. The reason it's 2 is this. If you have one positive item in 3D, one negative item in 3D, the large margin separating plane is just the plane that is perpendicular and bisects the line between the 2 points. So plane is going to be here. But the way you think of it is, if you change these 2 points as a teacher, you drive or you control that separating hyperplane however you want. Does that make sense, right? So you can drive it to fit exactly what W star you would want. Okay, so that's of course not surprising, but it's just like a very different way to think of this, different from learning perspective. And also I like this way of thinking of teaching as controlling what the final decision boundary will be. It will come up more prominently if we think of the learning system, the learner now, as a sequential learner. So different than previously, now the learner does not receive a whole teaching set or training set all at once. So for example, we can think of the learner as doing gradient descent on input x, t, y, t, one at a time. Okay. What does that mean? Well, the learner starts with a initial W0, and in each step, the teacher gives x, t, y, t. We can think of this as a control problem because there is a dynamics, and this is just gradient descent with eta as the step size. And this is actually just for the special case when the learner is doing these square laws. Okay, so it reduces to that. So that's how the learner would update its W. But we now think of W as the state of a dynamical system, and we know the dynamics. Okay, the teacher's job is to make the student arrive at a target weight eventually. So arrive at a target state eventually, but can the teacher do it with the shortest control sequence? Okay. If the teacher knows everything else like W0 and this dynamics, and the control, the x, t, y, t it can use are all bounded. Okay, that becomes an interesting problem, right? So that is a time optimum control problem. No closed form solution, but you can use binary search to write down a feasibility problem for a given time horizon t. You want to see if there is a feasible set of x, y controls to do this. Don't try to read it too much into this, but that's what it is saying. Is it feasible? You can set this up as a nonlinear optimization problem. If it's feasible, you do the next binary search over t. So you gradually do that, find the smallest t. So not a very nice algorithm, but at least we can sort of do it. Yeah, I just want to show you that if you do this in 2D and start, that's W0 is there. This is the teaching target. This green line is the algorithm you just saw. It finds sort of an interesting way to control the trajectory. Turns out this is the shortest one compared to some other more straightforward heuristics, such as in each step, greedily get as close to the target as possible. That's greedy, takes longer, or just shoot straight toward the target. That's also longer. All right, so we just mentioned this teaching extended to sequential setting, and that becomes much more like a control problem. I'm going to take, I'm going to zip through some of the remaining slides in the interest of time. You can extend the same teaching story to more interesting learners, for example, reinforcement learning agents. And now the goal, though, is for the teacher to teach a particular policy PyStar to that agent. And again, kind of we need to know what the agent's learning algorithm is. For example, if the learner is doing standard Q-learning in reinforcement learning, then we can do it. The steps are a bit more involved. So I have 2 minute slides on this, but the point is this. Q-learning basically maintains a Q table for each SA, and it's going to update that SA's entry if it is at ST and it performs action AT, such as going up, by this really messy equation. But if we give the teacher, or perhaps more like an attacker, the ability to poison or modify the reward that this SA step produces. So that's changing the reward RT circled in red there. You can ignore everything else, but imagine if the teacher makes RT artificially much larger than what it really is, then just intuitively, that ST-AT entry is going to be much larger. Okay. This is useful because the policy is really controlled by the ranking of ST-AT with respect to ST and all other actions. So all the other actions value stays the same, but AT's value gets boosted up if the teacher makes a fake really large reward. That will make AT look like the desirable action for the next iteration. So that's how the teacher can drive the policy by doing reward poisoning. But I'm not going to go into too much detail. There's a lot to talk about here. It's very difficult to do that because the teacher first need to get to each state to change that. And getting to each state requires forcing the learner to go to that state against its will, if you will. That requires teaching first a navigation policy to force the student to go to a hard to get to state, and then teach, then come back, and so on. Yes.
Is there any connection to things like apprenticeship learning, RL, where you're learning from demonstrations?
Yes.
There is a teacher in the loop and you want to give an optimal number of demonstrations?
Yes, there's a strong connection, but this is different. The difference is, again, in the nature of the RL agent. In the standard apprentice learning or imitation learning or learning from demonstration, behavior cloning, that type of setting, the student is willing to accept the teacher's demonstration, meaning that its algorithm has built-in copying mechanism, basically, to directly copy or indirectly copy what the teacher demonstrated. On those type of RL agents, it's actually much easier to do teaching or control, okay, compared to this type of learner, which is doing standard reinforcement learning, such as Q-learning. That's why there's all this complication.
No, I understand that. I'm just wondering if there is results similar to that of teaching dimension, where you can talk about what's the optimal set of demonstrations to give for a willing learner,
yes,
to converge quickly.
Yes, yes. The short answer is yes. But again, it depends on the limitation we put on the teacher. For example, can the teacher access state at will, or must the teacher follow the underlying Markov decision process to go to states? And that will affect the sample complexity a lot. So as you can imagine. But if, for example, in the strongest teacher is the teacher can just demonstrate arbitrary state and what's the desired action pair, that is almost trivial. You basically just need to, in the tabular case, you demonstrate each state's desired action for that policy. That's it. And so there's a strong connection there to supervised learning, because this demonstration of for each state, what's the desired action is no different than for each X, what's the desired label Y. Okay. But when you limit the power of the teacher so that it cannot get to each X easily to do the demonstration there, cannot get to each state, then that becomes much more complicated. Yes, so happy to talk afterwards. All right, reinforcement learning. Let me also say that this thing can even be extended when your students are not students, but they're game playing agents. So the teacher is not a player now, but the teacher is trying to change the behaviors of the players. Or in other words, here's a example of an unusual rock, paper, scissors game with 5 actions. So I don't know how many of you have heard of this, but this is the standard sub game for rock, paper, scissors. But then you have 2 more actions, fire and water. Fire is so powerful, it beats everything except water. And water is weak, it can only beat fire. It loses everywhere else. It turns out the Nash equilibrium is unusual. It's 1/9, 1/9, 1/9, a third here. Okay, so that's fine. This is a standard game with a known Nash. But the setting in teaching we're considering is, can the teacher teach any fake Nash equilibrium for this game? Any fake one, P star, Q star. And P star, Q star can be mixed Nash, doesn't need to be pure, okay? And so there are some technical conditions I'm not going to get into that to enforce this. It turns out you can find this solution through an ugly nonlinear program. But for example, if the teacher wants the P star, Q star to be both uniform distribution 1/5, perhaps with the argument that this is much easier for game players to actually use, like humans to actually use. The task here really is to design a game so that you start with the original game and try to change the entries as minimally as possible, say measured by 1 norm difference, okay, such that this target PQ is the unique Nash equilibrium of the final game. Okay. And so for our target PQ, it can be shown that, that's the minimum change here. All right, so still have 2 minutes, I can do it. I want to take a bit more time on this particular problem because I think it's very interesting on one hand, and on the other hand, I really is here to pick your brains. So here's the problem, okay? I have a symmetric one-dimensional distribution P supported on -1, 1. I draw n ID samples from it, okay? So these are my dots, like endpoints, right? The job is I want to select a subset of these points. I'm given this point, I'm the teacher, but I cannot choose points now. Nature draws endpoints for me. That's called a candidate pool. I must select a subset of those such that the summation of my subset is close to 0. Okay, so in a way like teaches 0. Okay, so as you can immediately see, of course, this is a like approximate version of subset sum problem. And to the machine learning crowd, this is training set distillation because the original data set, the candidate pool, you can think of it as the original IID training set. The question is, can the teacher help by selecting a subset of the training set? What does it mean to help? Well, it turns out this is going to be a super training set in that using the whole training set actually is worse than if you select a subset carefully. Why? If you use every point, because they're IID, on the reasonable assumptions, you get the summation of those, or actually the average of those is going to be 1/√n. But if the teacher simply chooses the item that's closest to 0 and use that as a subset, it's already getting a slightly better rate 1/n. Again, because there are n items. Imagine it's uniform P. But the teacher can do better by considering a subset of 2 and find the most symmetric pair of points. Okay, and you can get 1/n². Why stop here? Subset of 3, 4, 5, right? But we run into, of course, computational problems because you don't want to enumerate all those subsets. So what is a good way to do that? So this is where we have to think of, or we had to think of approximate algorithms. And here's one particular one where the teacher could divide the original interval into symmetric number of bins. I'm using 4 bins, symmetric, evenly spaced bins. I'm using 4 for illustration. And what the teacher can do is the following. It will take a pair of bins like the blue left bin and blue right bin. There are 3 points in the left, 2 points in the right. The teacher randomly matches 1 point from the left blue and 1 point from the right blue, and kind of marry them together, and they produce, the summation is the offspring. Okay, that's the offspring there. And then the 2 points disappear, right? You repeat this process until the one of the blue bins is empty. Okay, so you will have a number of offsprings here. Do the same thing for the pair of red bins. Okay, again, produce offspring here. So one observation is all these offsprings, they're the summation of the 2 parents. They must live kind of here. Okay, they have a narrower range. Actually, the more bins you have, the narrower the domain is for the next generation. Okay. Then you repeat the process, divide this generation into symmetric bins and do the marriage again. Okay. So the trick is if you select the number of bins carefully, then you can ensure 2 things. One is if you start with n points, you can roughly ensure you can run this process for log n generations. You still have points to, to sustain log n generations. And at the same time, the bins in each, the domain in each generation shrinks quite a bit. So through log n generations, eventually you get this type of guarantee that you get n to minus log n summation. But the time is only, for the algorithm, is only n log n. Okay. I want to mention this because, sorry, I'm running out of time, but I'm concluding this. I want to mention this because this is very typical of what you run into in machine teaching problems, because we are really dealing with hard combinatorial situations. So very often you hear things like set cover, subset sum, bilevel optimization, all those beasts. And I think one important way to think of this is to utilize approximation guarantees and just do that in a practically efficient way. So that's what I want to say. And for the sake of time, I'm going to stop here. And yeah, thank you.
All right, I guess we have time for perhaps one quick question. If there's any? Right, if not, we'll switch over to our next speaker. Thank you, Jerry.
Thank you.